Okay, so my second lecture will be on asymmetric dark matter freeze-out. But to remind you of what we saw in the previous lecture, we saw the Boltzmann equation. Let me write. Okay. And we rewrote this as a where we parameterized out the temperature dependence of the thermally average cross-section so that we could get a neat analytic solution. But of course, if you were solving it numerically, you wouldn't need to do that. You could put the full temperature dependence in there. Okay, and we labeled all this as lambda on x to the 2 plus n. Okay. So then we looked at the behavior of the solution. And we saw that to get the correct relic abundance of dark matter, we needed freeze out to occur at roughly, let's say, 20 to 30, x of 20 to 30. And then we found by taking our value for the departure from thermal equilibrium, this parameter delta, this y minus y equilibrium, we found this at freeze out, and then argued that after this point, this second term here in the Boltzmann equation, which we'd rewritten in terms of this delta, was not important. And then after that, we could just analytically integrate from this freeze-out point to infinity. And then let me write the... Oh. Where's this? Sorry. Yeah, and we found that the solution that that y infinity went as n plus 1 xf n plus 1 on lambda, okay? And now lambda has this m dark matter in there. So to get the correct relic abundance, we needed this to be roughly 0.43 electron volts. And then because of this, you know, the m here cancels off with the mass in the inverse lambda. And so then the cross-section you need becomes roughly independent of the mass. Because in our determination of x freeze out, there's only a logarithmic dependence on the mass. Okay. So from this, then you can see if you plot m dark matter and the required cross-section. So basically you see that at high masses where there's all the degrees of freedom of the standard model are in the plasma. You see, for the case of indistinguishable dark matter particles, you see here, this is about, this value here is about 2.2 times, no, let me write it. This is about 2.2 times 10 to the power negative 26 centimeters cubed per second. This is like, say, at the 1 TeV or so. And then at low masses, around 10 GeV or so, if you look at the solutions, basically the number of degrees of freedom then starts dropping, yeah, at freeze out. Because the freeze out is happening at a factor of 20 to 30 below the temperature. And you start getting a slight increase in the required cross-section. But this is like an order 1 factor or something, right? So this is the sort of picture. Okay. And now what we want to do is look for what happens in the case of asymmetric dark matter. So far we always took nx bar and nx to be equal. So now we're going to relax that assumption. So, okay. So in this lecture, I'm just going to assume that there's an asymmetry in the dark matter particle antiparticle sector. Yeah? So and then tomorrow we'll talk about how to generate such an asymmetry. Okay. So now let's introduce an asymmetry. So from now on, I'll just rename our x as with a plus and a x bar as minus, okay? So then the dark matter density, I should say, yeah, in the case of where you have distinguishable particles, so x is not x bar, then basically you get a factor of, you get the same requirement for the cross-section, but just a factor of 2 larger, okay? Okay, very good. Now, the dark matter density is now, we can write as m times the entropy density times y plus plus y minus, okay? So this is the particle number density plus the antiparticle number density. And this, we're going to have ms, eta. Eta is the asymmetry in the dark sector. And when we see the symmetry in the visible sector, now I'll write it with a subscript b, plus 2y minus. Okay? Well, this isn't very clear. Okay. So eta is just going to be our asymmetry. Okay. And this is going to remain fixed by assumption, right? So we've produced an asymmetry at some high temperature, then all the dark matter particle, dark matter particle number changing interactions. So this is going to remain fixed, yeah? So there's going to be like an analogy to the baryons in the visible sector, okay? So like at low temperatures, the baryon number is fixed. The baryon asymmetry, now we're going to fix also the dark matter asymmetry, okay? So we'll assume this is conserved at low temperatures, but we're going to have, it's going to be useful to introduce another parameter, which is just the ratio of the two. So y minus over y plus, okay? And this is going to be, is going to change with x, or the temperature, yeah? So at very high temperatures, say, at very high temperatures, these, even if there's some asymmetry, these could be very close because these y's will take their thermal values. And then afterwards, we're going to start annihilating away these y's. The total number density is going to drop, but there's still going to be this asymmetry, yeah? And then we want to solve sort of these equations in the presence of this asymmetry, okay? Okay. Okay, so then just a rewriting here, this will come in useful later. Y plus is just going to be eta on 1 minus r, and y minus is going to be equal to eta r on 1 minus r. Okay, and rho dark matter will just be ms eta plus 2 eta r on 1 minus r. Okay, and the baryon density is going to be given to a good approximation by the proton mass S times eta B. So what happens in the baryonic sector is that there's a very large annihilation cross-section between nucleons and antinucleons. So basically, all the antinucleons, all the antibaryons disappear, and we're left with just the baryons, which is the density is set by the asymmetry, right? And you can see here, in this case, if R becomes very suppressed, so Y minus is very small at late times, then again, our dark matter density is just going to be set like the visible matter density, okay? But we're going to allow for finite R, and then we'll see how this final density depends on the cross-section and so on, okay? So we'll be able to go smoothly then from the symmetric dark matter scenario to the asymmetric dark matter scenario at low temperatures. Okay. So our task now is, okay, so the observational constraint, if you like, is that omega dark matter and omega baryon is the mass, the dark matter mass over the proton mass, eta on eta B, and then some corrections allowing for finite R. To R infinity on 1 minus R infinity, okay? Or Okay, so now our task is to calculate R infinity, which is R when at late times. Okay. Very good. Okay. So now again, we'll just have now our equations for the dark matter densities. And we'll have this is equal to negative lambda on x2 plus n, y plus y minus. So it's just this same equation, okay? Minus y equilibrium plus y equilibrium minus, okay? Now we're going to write these equilibrium number densities. So these number densities are the number densities of the dark matter particle and antiparticle as long as the annihilation rate is very large, okay? Much faster than Hubble. Oh. Psi of x. So we're just going to parameterize these chemical potentials as psi. And this should be, okay, this chemical potential here is just the one in equilibrium due to the asymmetry, due to finite eta. It's the full chemical potential will be when, we'll consider when these freeze out, yeah? That's what we're looking for. But these ones are just due to the particle-antiparticle asymmetry. And that's why they have this plus minus sign, yeah? So when this thing is in equilibrium, x bar is annihilating rapidly, say to standard model particles, such as eventually to photons in the thermal bath, and here the chemical potential is 0. So when the annihilation is rapid, we'll have the relation that mu x plus mu x bar, which are these equilibrium chemical potentials. These have to sum to 0. Okay? Let me write this. Equilibrium. Okay? But they're not each, okay, they sum to 0, but they're not 0 because of the asymmetry. Okay? Okay. So now we have this parameter r, and we want to rewrite this. It's convenient to rewrite this Boltzmann equation in terms of r and track r as a function of x instead. Okay? And I should say, yeah, a useful reference is it's a paper by Grasser, Shoemaker, and Vecchi, which is 1103.2771. Okay? Okay. So now we'll start, okay, rewriting our equation in terms of this r. So now we want to find dr dx, okay? So just, yeah, and r is just, by definition, this. So take the derivative with respect to x of this, okay? And you'll find that it's just 1 on y plus, then dy minus dx minus r dy plus dx. Okay. And now we're going to use the, plug in. Here we have the equations dy plus dx and dy minus dx. Okay. And so then you can just plug in those into here. Okay. And you should find then that this is equal to, so here these are the same, just that you have this minus sign and this r. So we get -1 on y plus, lambda on x 2 plus n, y plus, y minus, minus y ek, plus y ek minus, times 1 minus r. Okay, I should say, even though I'm writing here y ek plus and y equilibrium minus, this is just equal to y equilibrium squared. Okay. Then, what you want to do is now rewrite this equation using, substituting in here for y plus and y minus in terms of eta and r. Okay? Yeah? It drops out of this term here. But let's see. Let's see. When we, let's see where it comes back in. They'll basically, we'll find it again soon. Yeah. Okay. So now, I won't do all the steps. So use these definitions here. Rewrite stuff. It's just an exercise of rearranging a few terms. Okay. And then, you should find then, something like dr dx equals negative lambda eta on x 2 plus n r minus y equilibrium squared 1 minus r squared on eta squared. Okay, so it's just a rewriting. Okay. Now we want to introduce r equilibrium. Okay, and this is just going to be y minus equilibrium over y plus equilibrium. And this is just going to be e to the negative 2 psi of x. Okay? And you see here we have this factor eta squared on y equilibrium squared. And this is going to depend basically on rewritten in terms of this r equilibrium. Okay? So, another crucial relation is that eta, which is equal to y plus minus y minus, is also equal to y plus equilibrium minus y minus equilibrium. And this is just equal to y equilibrium 2 sinh psi. And put an x here. Okay? So then what we want to do is find the eta on y equilibrium. Okay? So using this, you can show just that, just another little exercise of rewriting things. There's no difficult mathematics involved or anything like this. This is equal to y r equilibrium, 1 minus r equilibrium, all squared, okay? So then we substitute this into the above Boltzmann equation, and we'll find that this is equal to negative lambda eta on x 2 plus n r minus r equilibrium, and then this factor here, 1 minus r on 1 minus r equilibrium, yeah, squared. Okay, good. Okay, and now this is what we want to, this is the form of the Boltzmann equation which we want to use to get an approximate analytic solution, okay? So you can kind of see what will happen roughly, okay? At high temperatures, again, the annihilations will be very rapid, and R will track close to its equilibrium value, okay? And then we'll get a departure from equilibrium, and R will freeze out. Yep. Okay. I should point out, obviously, when there's no asymmetry at all, this thing won't, you won't be able to use this, right? It's only when you have some finite asymmetry. But we'll see that it will still allow us to go smoothly from the asymmetric case to the symmetric case, from what we learned also in the last lecture. Okay. So this, now we want to find an approximate analytic solution. Okay. Okay. So the sketch of the behavior is the following, yeah? So we had our solution in the symmetric case, which did something like this, which was for y plus equal y minus, yeah? Or in other words, eta equals 0. And now we want to solve a very similar equation that we've just rewritten in terms of this r and just rewritten this in terms of r and r equilibrium. But when we solve that, we'll be able to go back into y plus and y minus very easily. And the picture will be the following, that, up here, this is sort of like, you have to imagine this is like a logarithmic plot, yeah? So up here in thermal equilibrium, the numbers are very large, and there's overall a little difference between y plus and y minus compared to their full values, yeah? The difference is small, yeah? And then, so if you plot, imagine you plot them, then you won't even, on a logarithmic plot, you won't even see the difference, yeah? But then they'll start annihilating, and then they'll freeze out, and you'll have something like this. So you'll have now we'll have both y plus and y minus. So while y plus will do something like this, and now y minus might do something like this, yeah? So this difference is always fixed, but if you imagine this is sort of like a logarithmic plot, so this is like maybe 10 to the minus 3 here, and this might be 10 to the minus 10 or something like this, then you start at after the freeze out, you start see, the asymmetry becomes important as long as the cross section is large enough, yeah? So you really start suppressing these dark matter antiparticles compared to the dark matter particles, and of course, the more you suppress this, the more this value here goes just to eta, yeah? The more you suppress the y minus. Yeah?
For me, it's a little bit confusing because you have only one differential equation.
Yes.
And you are obtaining two solutions of one differential equation.
Yeah.
How?
Yeah. Okay. I mean, just imagine you have a solution for y plus, and eta in this scenario is fixed. So the difference between, so imagine you have a solution for y plus, eta is fixed, then and y plus minus y minus is just eta. So then you immediately get a solution for y minus. Yeah?
Oh, okay.
Yeah.
Okay.
Yeah. It's because we're interested in the low temperature behavior once an asymmetry has already been generated. So this is fixed. Yeah?
I understand, because the freeze out, it will be fixed, but before not, before you vary. So...
Yeah, no. During this entire process, we're considering eta to be fixed. During this entire freeze out annihilation process.
Like an imposition.
Yeah. And this will be set, we imagine it's set at a higher temperature, and I'll discuss mechanisms for where this is set tomorrow. Yeah.
Okay.
Yeah. We're working from sort of low temperature to high temperature because I wanted to introduce the Boltzmann equations for the symmetric case first. So, as an introduction, yeah. I should say, when you're solving, in general, when you're solving, if you were solving also allowing this to vary, then of course you'd need to solve some coupled differential equations, yeah. Okay, so to obtain this solution, basically solving for R is just equivalent, yeah? And at early times, R will be approximately R equilibrium, okay? And later on, I should write here, later, so after this freeze out, later R will have trouble tracking our equilibrium, and this will be our freeze out, yeah? Okay. Okay. So, yeah, okay. So now we have this equation here. Now imagine we're past the freeze out point. So R has departed, we'll say significantly by some order 1 factor from R equilibrium, yeah? So we'll say, what happens here? So then, basically, we can ignore this second term here. So then, okay, let me explain a bit more. So imagine R is getting larger and larger compared to R equilibrium. This is sort of freeze out. And R is going to be, less than 1, yeah? Here. Okay. So here we can still ignore this overall term, okay? So then we'll just write, we just want to get an approximate analytic solution again, okay? And then we're going to make some rough estimates like yesterday, but of course you can also solve this numerically. And so you can check that your sort of approximations you might have some questions about that they're working out. Yeah. Okay. So then after freeze out, we're just going to have this x2 plus n. Did I miss an r? Yeah. Yeah. I missed an r in my notes, yeah. Okay. Or just that d log r dx negative lambda eta on x2 plus n. Okay, now we just integrate both sides from x freeze out to infinity. D log r equals negative lambda eta x freeze out to infinity 1 on x2 plus n dx. Yeah, I should say here. I should write here. So we're considering here. After freeze out. Okay. Okay, and so that we don't forget, let me just, it'll be useful, just let me write this equation here that we're going to want to solve. Just let me write it here. R minus R equilibrium 1 minus R on 1 minus R equilibrium squared. Okay, this is what we're going to solve. Okay, very good. So, okay, now we just integrate both sides and find, of course, that log R infinity over R at R subscript XF just means R at freeze out. And this is equal to, let's say, so do the other integral, plus lambda eta on n plus 1 on x n plus 1, of course, xf to infinity, which will give us negative lambda eta on n plus 1 lambda eta on x n plus 1 on xf n plus 1, okay? Or in other words, r infinity will be roughly r at x freeze out. And I'm going to approximate this as the equilibrium value even. exp negative lambda eta on n plus 1 on xf n plus 1, okay? So what you notice now from this rough analytic solution is that r infinity depends now exponentially on this factor here, all right? And remember, lambda contains the cross-section, yeah? So now it's gonna, our value for r infinity, which is the y minus over y plus, is exponentially sensitive to the cross-section, yeah? Okay. Now, okay, we have this. Now we need to estimate xf, yeah, the freeze out time. As you can see, the strategy of solving this is very similar to the symmetric dark matter freeze out case we saw yesterday. Okay. So to estimate this, we're going to say that, okay, before freeze out, up until freeze out, dr dx is going to be approximately dr equilibrium dx, and then that this is going to be approximately negative delta lambda eta on x n plus 2 equilibrium, where again this delta is just going to be some order 1 number, okay? Basically, yeah. So now looking at this, let's see, looking at this freeze out, yeah. Basically, when to see this, okay, say dr dx is all of this here, yeah? Now, imagine that, you know, we're in the tail here, so r and r equilibrium are suppressed, much smaller than 1, yeah? So this factor isn't important here, yeah? So we just have r minus r equilibrium, yeah? And then when this thing here is approximately, when r, all I've done here is set r minus r equilibrium to be equal to delta times r equilibrium. So maybe I should write it like this. Delta r equilibrium, or maybe just to get the point across, what we've done. So this is just the prefactor here, and then we set this r minus r equilibrium to be delta some order 1 value times r equilibrium, yeah? Some order 1 number, okay? That's all it is. Very sort of simple estimate, yeah? Okay. So then we have now, so then we have the R equilibrium dx is approximately delta lambda eta on x2 plus n R equilibrium, okay? Did I get that point across, or was David, did you see what I did? Okay. So, say when we're in the tail here at around the freeze-out time, yeah, R and R equilibrium are very suppressed, way below 1. Okay, so then we just cover this here. Okay, so that term is 1. It's a very good approximation. Then we have the R dx is this times R minus R equilibrium. Yeah? And we're going to define our freeze-out time as when R minus R equilibrium is like an order 1 number times R equilibrium. Yeah? And this order 1 number, we denoted delta. Okay? And we say still that we approximate that the R dx is still roughly the derivative. Yeah? And this will allow us now to estimate the freeze-out value of x. Let's say here. Okay. Have I? Yeah. Very good. Well spotted. Okay. So now we're going to use that. Yeah. Okay. Now use the 2 sinh psi of x is equal to eta on y equilibrium. We saw this before. Psi of x is equal to arc hyperbolic sine eta on 2y equilibrium. Okay. Okay, and then you can, yeah. Okay, how does this, let me see. Now we want to find, okay. Yeah, okay. So now we want to find, basically what we want to find is this factor here, the R equilibrium dx, yeah? R equilibrium is e to the minus 2 psi of x, yeah? So to find this, we want to find this derivative and then equate it to this side and then solve for the freeze out, yeah? Okay? So we have this. Now, you can remember that y equilibrium is a g x to the 3/2. A I defined the last lecture. It's like 0.15 or something, yeah? E to the minus x. Okay? And we had last lecture also that dy equilibrium dx is equal to negative y equilibrium 1 minus 3 on 2x. Okay? So now the task now is to evaluate dr dx using all these things, yeah? So dr equilibrium dx. So I leave that as a exercise, yeah? The steps are given in my notes. So we'll keep the diagram, and so I'll continue over here. So, okay. So, okay, so then you should eventually find that dr equilibrium dx is simply negative 2r equilibrium hyperbolic tangent psi 1 minus 3 on 2x. And our freeze-out condition then is that this is equal to this side here. Which was negative delta lambda eta r equilibrium on x2 plus n, okay? So now we can cancel off these r equilibriums, okay? And simply find that the freeze-out condition becomes that tangent 1 minus 3 on 2x f is delta lambda eta on 2x f n plus 2. Okay, first of all, we're going to, xf is like order 20, 30, so we're going to ignore this term. And for small psi f, okay, for small psi f, this is going to limit somewhat the range of where our analytic solution is valid. Hyperbolic tangent psi f is approximately hyperbolic sinh psi f, which you remember is just eta on 2y equilibrium, okay? So small psi f means that this should be small, okay? So then substitute this into here, okay? And lo and behold, so substitute this into here, and lo and behold, you have eta on 2y equilibrium equals delta lambda eta on 2xf n plus 2. Okay? Now, something interesting happens. The asymmetry parameter also cancels. Yeah? So then you find that xf, okay, substitute in y equilibrium is a function of xf. Yeah, it's just this Boltzmann suppressed thing, right? So again, we find that xf is simply log delta lambda a times the degrees of freedom of the dark matter minus n plus 1/2 log approximately log delta lambda a g, okay, which is independent of eta and the same as for symmetric dark matter freeze out. Okay? Yeah. Yeah, but we're interested in a scenario where, yeah, this is going to limit the range of our validity, yeah, and it's going to be when eta is not too far away from Y equilibrium. See, what happens if eta is much larger than Y equilibrium, we'll be in the range of the solutions where the final density is just set by eta. So then we've gone smoothly, at least, from the symmetric case to the asymmetric case, and then our analytic solution won't hold anymore, but we know what's happening out there. Yep. Okay, very good. Okay, the same as for symmetric dark matter freeze out. And okay, you can set like for symmetric dark matter freeze out, you can set delta to be basically n+1 to get a good approximation. Okay. So then, as we had before, R infinity, now, yeah, we know how to find X freeze out. So R infinity is just going to be R equilibrium at X freeze out approximately, and then an exponential suppression, which depends on the parameter lambda, which has the cross section in it, and so on. Lambda n+1, 1 on xf n+1. Okay, very good. And this, okay, to answer your question, this is a decent approximation until, let's say, good approx up to R infinity down to, should say, down to R infinity about 10 to the minus 4 or so. Yeah, it's like within 5% or something to the numerical simulations, and I think it's decent, also a bit lower. Yeah. Okay. Okay. Very good. Now, okay. Okay. Okay, good. So now we want to compare this. So to get, down, we want to rewrite this exponential term here. It's in terms of negative lambda eta, which contains the cross section, so on. It's not very transparent, right? So there's a neat way of rewriting this in terms of what we know, the cross section we know and love from symmetric dark matter annihilation. So that's what we're going to do. We're going to rewrite this factor now to a very enlightening form, okay? So for asymmetric dark matter, yeah. Okay, yeah, so we want to keep this, yep. Okay, now for asymmetric dark matter, we saw the relation before. Asymmetric dark matter. We saw the relation before that we had the relation M over MP. Epsilon is equal to 1 minus R infinity. I'll define this epsilon in a second. Omega dark matter over omega baryon, yeah? Where this is like 5 or something, yeah? Epsilon will just be the ratio of the asymmetries. Okay. Now to match onto yeah. Sorry, MP. What do you want? M here. This is dark matter mass. This is the proton mass. Yeah. Okay. Okay. We want this to hold to match observations. Yeah. So we can't have arbitrary M dark matter, eta, and R infinity. Yeah. They're related observationally. Okay. For symmetric dark matter, epsilon is 0, R infinity equals 1, and we have 2y infinity M dark matter. The factor of 2 is just because we have x and x bar. Eta B MP is equal to omega dark matter over omega baryons, okay? Or this factor, okay. So yesterday I told you this has to be 0.43 EV, yeah? Well, here we have an extra factor of 1/2, yeah? Because we're dealing with just one of the components of the symmetric dark matter, okay? So we have this, and now we know from what we saw yesterday, we had this nice formula, right, that M dark matter y infinity is equal to n plus 1 xf n plus 1 on. Now we're going to consider having symmetric, we're going to compare asymmetric dark matter and symmetric dark matter with the same mass, but different cross sections, yeah? So the same mass. So now instead of just writing lambda, I'm going to put lambda symmetric, which is just the cross section required for the symmetric dark matter case. Okay? And lambda symmetric pi on 45 m Planck m dark matter sigma, let me call this sigma n WIMP. Yeah, for the symmetric, the well-known cross-section for symmetric dark matter, which we derived. And then we have a factor which is like G star S on G star radiation 1/2. And here I got sick of writing this, so then I'm going to just write it as G star effective to the 1/2, okay? Now we're going to equate this thing with this, yeah? So we're going to make this here equal to this, okay? This is MP, okay? And so then we'll find, so it's really just this equal to this with the lambda substituted in, okay? And then you just rearrange it and find the required WIMP cross-section, yeah? This is sort of what we spent yesterday deriving, huh? But now it's, yeah, rewritten in terms of the proton mass, M Planck, G star effective to the 1/2. At very high temperatures, this is like 10. 180 over pi, omega beta over omega b over omega dark matter, eta b. Okay, so this is just the required cross-section for the symmetric dark matter case rewritten in terms of these observed values, yeah? Now we had here, for our asymmetric case, we had this factor here, which is very similar to here, just instead of having lambda symmetric, we have lambda, yeah, which has a larger cross-section, as we'll see in a second. Okay, so we're going to write lambda, we're going to write as lambda symmetric times our annihilation cross-section for our asymmetric dark matter over sigma n WIMP. Okay? So then we find that R infinity will be exponential. Now we're gonna just substitute in this thing here for sigma n WIMP. Okay? And we're gonna find that this whole thing boils down to having, okay, negative, yeah, let me do one extra strip. Lambda symmetric over n plus 1 xf n plus 1 sigma n over sigma n WIMP. Okay? But this combination here, you can use what's on the other board to find that this is equal to exponential negative eta 2 on eta b, omega b on omega dark matter, m dark matter over proton mass, sigma n over sigma n WIMP. Okay? And then, again, rewriting stuff using this relation here. I let you check, okay? It's really just a simple rewriting. We find that R infinity is equal to exponential negative 2 sigma n over sigma n WIMP 1 minus R infinity over 1 plus R infinity, okay? Okay, so now you say, okay, what's the point of that? Because now we have R infinity on both sides. But the point is that, okay, here you have, if R infinity is not very close to 1, yeah, this thing will just be 1, and then you'll have this approximate behavior that R infinity scales exponentially like this, you know, the typical annihilation cross-section, the annihilation cross-section over the WIMP cross-section, yeah? So in the end, so this is sort of a very neat result, which lets us see the behavior for what what annihilation cross, so what we've derived now is what annihilation cross-section we need at low temperatures for asymmetric dark matter. Okay? So basically a small change in the cross-section is enough to massively suppress R infinity from 1. Okay? So then we have, you can have a plot like this. So here is M dark matter, 10 GeV, 100 GeV, 1 TeV. So I'll just sketch the solutions. So this is to get the correct relic abundance. For the symmetric dark matter case, it does something like this. Yeah. And then you have a factor of about, if you multiply this, so this will be, this value here is like 4.4 times 10 to the minus 26 centimeters cubed per second, because we have both particle and antiparticle distinguishable. And if you want to go from, this is symmetric dark matter with R infinity equals 1. And if you want to go to R infinity equals 10 to the minus 2, all you need is a cross-section that's about a factor of 2.6 larger or so, okay? And if you want to go to R infinity 10 to the minus 4, you'll find that you need to have a cross-section about 4.6 times larger. Okay. So, very good. Okay. So the consequences of this, huh? Yeah? Is this independent of eta? Yeah. So we've cancelled off eta by requiring the correct relic abundance. So there's a relation here between eta, M dark matter, M, all these things, and rewritten in terms of, I've just rewritten in terms of R infinity. So given a certain mass, and given a certain mass and R infinity, okay, the observations imply a certain eta. Yeah, so that's sort of hidden in this relation. Yeah. Otherwise, you can also go, if you're given M dark matter and eta, to get the correct dark matter density, that fixes R infinity. Yeah. 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 We took this to be roughly 1. Yeah. So at R freeze out, basically, in other words, Y minus and Y plus at R freeze out aren't yet really far apart. Yeah. And then later on, after freeze out, we integrated, analytically, and that's when they really depart. Yeah. Of course, yeah, you can improve this estimate by including this value here, right? But I've just done the simplest imaginable approximation. Okay, so consequences. So yeah, I've got a few more minutes. I also want to talk about the unitarity limit on dark matter, but I'll push that to the next lecture maybe. Okay, so let's see. So the consequences. Indirect detection. Okay. Imagine we have symmetric dark matter. Indirect detection means, imagine you have dark matter annihilating in the galaxy today or in a dwarf galaxy nearby, somewhere where the density is large. Then if it annihilates into and eventually produces standard model states, photons, and so on, then you can hope to detect them, okay? So this is just in the jargon known as indirect detection. So for symmetric dark matter, the flux of photons can be neutrinos, or it could be charged particles in principle, but there you have to take into account the bending of their path in magnetic fields. But so let me just write it in terms of photons. Neutrinos are just as valid, of course. So the flux you expect depends on the cross-section at the velocity of the dark matter in the object you're observing today, rather than the velocity it frees out. There's a statistical factor here depending on if x is equal to x bar. Yeah? If x is equal to x bar, you get a factor of overall 2 here. Okay, it depends on the cross-section. The spectrum of photons your dark matter annihilation produces, and the amount of dark matter in your sort of observed volume of the sky. So this sigma is just the observed sky area, okay? So why does it, and this is the dark matter density, which you can estimate from observing stars, stellar motions. And why does it scale as, this is sort of what we observe indirectly. So then the whole thing should scale as n dark matter bar, yeah? And so this is just this number density rewritten in terms of rho, which we can sort of estimate divided by the hypothetical dark matter mass. Okay, so that's why it has that scaling. Okay. Okay, now for asymmetric dark matter, the flux is going to be suppressed. Yeah? Just because we don't have as many dark matter antiparticles around to annihilate today. Yeah? So phi gamma symmetric is proportional to sigma v, the symmetric, sigma v for symmetric dark matter, n plus the symmetric dark matter number density, okay? And this is equal to, these two by definition are equal, okay? And this is equal to sigma v rho dark matter squared on 4 m dark matter squared, yeah? So each of these is half of the dark matter, so you get a factor of rho dark matter on 2 m dark matter for each. While for the flux of photons you're going to see for the same dark matter model, but now with an asymmetry. Okay, and then we're going to write this as sigma v r infinity. Okay, asymmetric dark matter, sigma v, n plus asymmetric dark matter, n plus asymmetric dark matter. So n minus is just r infinity times n plus, and rho asymmetric dark matter is just n plus asymmetric dark matter 1 plus r infinity m dark matter. So this r infinity takes into account the dark matter, any remnant dark matter antiparticles still around. So, and this is 2 n plus symmetric m dark matter. So the dark matter density is its sort of observed value. And so we get n plus asymmetric dark matter is 2n plus symmetric over 1 plus r infinity. So then we're going to have this ratio of the fluxes So your observed flux in asymmetric dark matter models compared to the observed flux if you didn't have an asymmetry, as we said, is going to be suppressed. In principle, this cross-section could be slightly larger, but doesn't have to be because, from what we derived before, to really suppress the dark matter antiparticle number density, we only need to increase the cross-section a little bit. And when you put everything together, it gives you this factor here. Okay. And so this allows you to see, okay, if r infinity is 1, we just get a factor of 1 here, and it's equal to the symmetric case. And if r infinity is suppressed, then you're going to massively suppress the flux you see. Yeah. So you can hope in certain dark matter certain models that maybe r infinity isn't too low. Maybe this cross section, the flux depends on the cross section, at the velocities you're interested in. Yeah. So if the cross section shoots up a lot as the velocity drops, which happens with Sommerfeld-enhanced cross sections typically, then you could maybe still get some sort of signal. But in the models that have been sort of looked at in the literature, you maybe still get some C and B constraints down to R infinities 10 to the minus 4 or so, but then afterwards the C and B constraints, even the very stringent C and B constraints, then in the Sommerfeld-enhanced case are no longer important. So practically speaking, even with models with light mediators, so you get boosted cross sections for indirect detection, the stringent CMB or Fermi limits with models with this Sommerfeld enhancement that then decay into standard model states disappear for R infinity below 10 to the minus 4 or so, which means that if your symmetric dark matter model is ruled out, if you have some symmetric dark matter model which is doing something useful, you're interested in, even if it's ruled out by indirect detection, in the case simple extension where if you have a particle-antiparticle asymmetry, this model might not be ruled out anymore. Yeah, very easily. Okay. Now, okay, and in the last minute, I'll just mention direct detection. Here, the rate can be enhanced compared to the symmetric case, but not necessarily by much. Okay, so how to see this? Typically, okay, for those who don't know what direct detection is, it's when you have typically an experiment in a low radioactive environment, deep underground, where you look for rare, you look for dark matter coming in and having some interaction with, and scattering a nucleon, okay? And you look for the nucleon recoil, okay? And the couplings which that enter this interaction and mediator particles and so on, can, in many models, are linked to the annihilation of are related to the annihilation cross-section, the same parameters and that are giving you the annihilation cross-section. So if you go now to asymmetric dark matter, you need to have a slightly larger annihilation cross-section, which means you need typically slightly larger couplings or lighter particles, yeah, to mediate the annihilation. And so you can imagine then the same parameters entering into the direct detection cross-section and increasing the rate a little bit. But you don't need to increase the annihilation cross-section by much to go to very small R infinity. But sort of R infinity, there's no reason for the cross-section to be close to the WIMP value. It could be much larger, yeah, in the asymmetric dark matter case. If it's much larger, then you just have Yx very close to eta, yeah? You just go into this limit. And then the annihilation cross-section could be many orders of magnitude larger than the WIMP annihilation cross-section, which means that some couplings which enter into your direct detection cross-section can also be much larger, yeah? So then it could be that the direct detection rate is very much enhanced. You can also get exotic signals, which I'll talk about tomorrow, such as induced nucleon decay, when the dark matter carries some baryon number and then some dark baryon number, and this induces then a nucleon decay instead. Okay? Okay, and that's it for today, so thanks.
Any questions for Iason?
Yeah, I mean, if you think about a generic WIMP,
yeah,
you're already a little bit under pressure because the interactions are too large, right? So with this respect, in principle, asymmetric dark matter doesn't help at all, right? So you need an even larger cross-section to be in the regime where the symmetry is even relevant, no?
Well, it's not always so clear, right? Because you go to you can construct models with where the dark, the asymmetric dark matter is annihilating to some secluded, say, a dark photon or a dark scalar or something like this. And then the portal linking these two sectors to the standard model can be very suppressed. And typically in these models, you need the light particle that you're producing in the annihilation. It's constrained by ineffective, yeah? So you want to get, but if it decays back into the standard model with a long lifetime, you still have enough space for it to escape. You're not sensitive with ineffective anymore. It just needs to sort of decay before BBN, and then you're safe. But these models, I mean, they were popular a few years ago, also to explain small-scale structural anomalies through self-interacting dark matter. And in those models, the C and B constraints of this dark matter indirect detection for the C and B constraints were very stringent. But if you went to R infinity 10 to the minus 6, then the C and B constraints went away. Yeah. Now, people have reevaluated limits from supernova and Kai Schmidt-Horburg and collaborators have improved the limits from BBN and so on for light, light stuff decaying, so you're not above the hadron dissociation cross section. So even that possibility is closed up a bit. Yeah. But we'll see tomorrow some example models where you seem to be safe for now.
Okay, very good. I think we can go for coffee, and then we'll be back for the discussion session at 5. Okay, thanks.